My name is Maria Banks, and I'm going to, let's see, I want to make sure I can see my slides here. Okay. So I'm going to talk to you today about the Lunar Reconnaissance Orbiter, or LRO, and in particular, our coverage that we're having of our landing sites. So my goal here with this talk today is to share awareness for the whole community of this wealth of data, new observations, old observations, and data products that the team is making as consistently as is possible for all of the different landing sites to enable comparisons between the different landing sites. They're also collecting this data before and after landing and as possible during surface operations. So this will hopefully facilitate interpretations of data that's acquired from the surface assets. Also, your investigations into understanding the influence on the lunar environment of these surface activities and any other investigations now and maybe ones we're not even thinking of off into the future. So anyway, I am a member of the LROC science team. I'm also the deputy project scientist for LRO, and I'm the lead for mission support. And so in that role, I decided to create a group of representatives from each of the LRO instrument science teams. And so those representatives are my co-authors on that you see on the slide here, but they're really just representatives. So this is really just a massive effort. So I want to just give it a shout out for all of the LRO science teams and all of their efforts to thoroughly characterize these landing sites for us. And I came up with the name for our group, the Lunar Reconnaissance Orbiter Landing Site Investigative Team. And because I work for NASA, I had to make that into an acronym. And so manipulated that into the acronym LANDIT for fun. Okay. I also just wanted to say really quickly that tomorrow is the 15th anniversary of the launch of LRO. So LRO was intended to operate for 1 year. So starting tomorrow, we begin our 15th year of operations. We are on our 5th extended mission, and we are already beginning preparations for our proposal for hopefully a 6th extended mission. So, and as you've been hearing so far today, we are just at the beginning of this wonderful, unprecedented and exciting era of lunar exploration. And so I just have a quick map here of our upcoming CLIPS planned landing locations. That's about 12 locations, including the Intuitive Machines Mission 1 from earlier this year. And my colleague and fellow project scientist, Brian Gary, is going to talk more about this later. And then, of course, Lori's and others have been talking about Artemis and all the extensive landing site planning and traverse planning, and of course, our upcoming crewed landings. And then our incredible international community of technology demonstrations, landers, rovers, sample return missions that are already being implemented and planned into the near future. LRO is actively engaged with supporting all of these efforts. And just a tiny bit of background for those of you that maybe are not as familiar with LRO. The LRO payload was actually specifically designed for landing site characterization, thus the name Reconnaissance Orbiter. And as I was mentioning, these new and existing observations, they're already actively being used for that landing site selection, for operations planning, for supporting these active missions. And as I was saying, just trying to share with you awareness of all this data to hopefully support your investigations into the future. So let's start with LROC. The LROC team has developed a list of standardized narrow angle camera, or LROC NAC images, and also derived data products from those images focused on these landing sites that are being acquired and produced as feasible for all the landing sites before and after landing. And so these include images with high incidence, such as, let's see if I can get this to work. So this is just an example of Mare Crisium. That's Blue Ghost Mission 1. That's a high incidence angle image. Some low incidence or very high sun images. That's Reiner Gamma, where a lunar vertex is going. And also oblique images, which personally are my favorite. And those are the Grathisen domes. That's where CP21 or Lunar Vice is headed towards. And then also, of course, geometric stereo pairs and feature mosaic images. And at some of these select sites, LROC is acquiring images to support photometric studies. So as I mentioned, LROC is acquiring geometric stereo images. They're using them to make DTMs and other products, such as some examples here. That's an orthomosaic, a slope shade map, and a color shade map. And the featured images are also being used to create controlled mosaics with increased spatial accuracy. Let's see. So just some stats for you for fun. In support of the CLIPS deliveries alone, LROC has collected 28 sets of stereo observations, 18 feature mosaic sets, and 10 obliques. And if we look at it as a whole for support, for mission support, LROC has created and released 45 DTMs with 2 more in progress right now. And that, of course, will be a continuing effort, and 49 controlled mosaics. So dig in and have fun. And just some additional examples. This right here is an oblique of Malapert Massif, just to remind you that even though LRO is no longer flying directly over the South Pole, it can still slew and view all the way to the South Pole. So we do still have imaging capabilities. And then this is just a fabulous 18 Rockanac, 18 Rockanac DTM mosaic of the growth eyes and domes. And also I mentioned active mission support. This is just one example here. This was an image that was taken as LRO's closest approach to the landing site for Intuitive Machines 1. And so this quick turnaround of acquiring this image just a few days after landing enabled the Intuitive Machines team to locate the lander in the image, which gave them the ability to confirm where they had landed, look at their illumination models, understand their power situation, and prioritize the remaining operations time. So just an example of how hopefully these images can continue to support these active missions. And for fun, Django 6, this was just released on Friday. This is LRO's observation. I think it was June 7th. It flew over the landing site and was able to acquire this image. So this is before and after, of course, images blinking. So Lola, so hopefully you've been able to look at Lola products in the past. They have a global geodetically controlled topographic map of the moon, global slopes and roughness at a range of scales, normal albedo zero phase reflectance, again, a global product, and global passive radiometry data sets. This is an example of South Pole topography from 80 South to the pole, and of course our locations of our candidate Artemis landing regions. So additionally, Lola has been creating new 5 meter per pixel Lola digital elevation models, or they call them LDEMs. And so that's been derived for several high priority South Polar sites. And then also DEMs are being created and are available over larger areas now, over multiple pixel scales spanning from 10 to 240 meters per pixel. And from these new and improved LDEMs, new derived data products have also been produced, such as a 20 meter per pixel map of permanently shadowed regions and roughness maps and such. And then also wanted to mention that these miniature retroreflector arrays, or LRAs, are being deployed on several of the CLIPS landers and also international landers. And so Lola was not designed to range to these, but they have successfully figured out how to do this. And just recently ranged to Chandrayaan-3, which we heard about this morning. And even with its orientation on the surface, was able to range to the LRA on SLIM. So let's talk about LAMP for a minute. Of course, if an observing opportunity should arise, LAMP will remotely observe the exhaust of a landing, which is important to provide insight into the associated migration of water and evolution of vapor through the exosphere, deposition of exhaust from the descent burns. We haven't really had a chance to do that recently with Intuitive Machines. Actually, the first line of sight to the landing site by LAMP was about 20 minutes after landing in a range of about 500 meters. So the combination of that range and the duration, even that short duration after landing, they were not able to pick up a signal. So it's a small window of opportunity, but we'll continue to take advantage of that should those opportunities occur. But also LAMP spectral albedo maps of landing sites are being created before and after landings. So that surface brightness changes determined with these maps can provide insight into the extent of the surface alterations due to those landings and the surface activities, which of course is going to be important for helping us predict the extent of the distribution of that rocket exhaust, a better understanding of that relationship between the lander dry mass and the blast zone area. And then also LAMP products can provide insight into mineralogical composition of the landing sites. So most recently, LAMP has been been found to be capable of distinguishing between plagioclase feldspars and mafic minerals. So other uses for these LAMP data products. Crater is looking at the lunar radiation environment, in particular before and during the peak of our current solar cycle, which is solar cycle 25, which will help us hopefully to more accurately predict the galactic cosmic ray environment that the astronauts will experience during the Artemis missions. And crater data is also being used to quantify the high energy particle radiation environment that's both the cosmic rays and the solar energetic particles that contribute to the sputtering volatiles from the surface of the lunar atmosphere, and that produces these free neutrons within the lunar regolith. So that's important, of course, for interpreting neutron signatures and using that to measure our subsurface water. And I also wanted to mention that Crater, of course, was operating from lunar orbit during the Peregrine Mission 1 mission, which had 2 instruments collecting, shall we say, complementary data. Those are the Neutron Spectrometer System, or NSS, and the Linear Energy Transfer Spectrometer, or LETS, which of course we're acquiring data at the same time from cislunar space. So some interesting comparisons can be made with, it's unusual to have those 3 types of instruments operating at the same time in different locations in space. So, Mini-RF is still continuing to operate, but in a bistatic configuration, which means that the instruments receives a radar signal bounced off the lunar surface that's transmitted by a ground-based antenna. And so radar data at 4.2 centimeters and 12.6 centimeter wavelengths in the X and S band respectively can be used, to understanding these sites, in particular, looking at rough terrain and rocks, looking at recent impact craters, and really importantly, the stratigraphy of the shallow subsurface. And so diviner data, hopefully you've all been able to use this diviner data to take a look at the temperature maps, rock abundance, and the H parameter maps. And wanted to mention that the team has recently optimized pointing and field of view modeling, which has enabled the creation of new higher resolution nighttime temperature maps and rock abundance maps, which enables identification of smaller and fainter thermal features. So this is just a view of the Apollo 15 landing site. This is a diviner rock abundance map from 2011, and just pay attention to where those yellow arrows are. So this is one of those recently optimized pointing field of view modeling efforts from 2023 rock abundance map. And you can see just an increased spatial resolution where those 2 arrows are. For this rill in particular, you can see that rock abundance is more focused on the slopes on the sides of the rill. So I just have 2 more slides. So this higher resolution temperature maps of landing site areas can also be created, been incredibly helpful with landing site selection efforts to understanding temperatures at different times when the instruments are operate. And to help with that, diviner is also acquiring higher temporal resolution imaging at those strategic times, like at lunar noon, to understand those maximum temperatures. And this is just an example of one of those efforts at the Grathisen domes. And then also a reminder that diviner team also has thermal modeling capabilities for the polar sites. So this is just an example of a 1-week modeling, and the red markers here are the actual temperatures to show how that lines up, and this can increase our temporal resolution. Also, diviner has the capability to view off nadir without having to slew the entire spacecraft. So the team is taking advantage of that capability to build up a data set of off nadir observations over multiple landing sites. And this is pre and post landing data sets. And this should be really helpful to investigate the lunar emission phase function, which can constrain the surface roughness of the landing site, and importantly, highlight potential regolith changes due to that lander activity. And so I'll just end on this slide with a view of QuickMap, which hopefully you're all familiar with. And I went a little crazy and turned on all kinds of layers, including, there's the Diviner Rock Abundance map up here, and the LOLA LDEMs, and footprints of different LROC locations of their featured image mosaics and geostereo pairs, and some mapping efforts. Anyway, just to remind you that this is a really great tool to not only access data, but to actually manipulate it and use it on a map. But of course, all data is available in the PDS too for your use. So thank you.